Hi, Professor Leggett. Do you hear us?
Yes.
Yes? Okay,
Yes.
hi, nice to meet you.
Yeah. One of the things I'd like to ask you,
Yes.
or request you, if you think I'm speaking too fast for the audience, please raise your hand. Okay.
Okay.
And so,
Okay.
and
I
I'll
will
try to slow
interrupt
down.
you if we think it's too fast. Okay, thank you.
Yeah.
So I'm just waiting people to come back from the coffee break and we
Yes,
start, okay?
Yes.
I do a brief presentation.
I can see the lecture theatre. Yes, and see
Okay.
people coming in.
Okay. So can we start? Okay.
Sure.
So welcome everybody once again for this second lesson on this of this afternoon program, this our afternoon of today. So for the second lecture, we have Professor Anthony James Leggett from the University of Illinois that is already with us here in the screen. And Professor Leggett is a theoretical physicist who have extensive contributed in a broad range of topics in condensed matter physics and to the comprehension of superfluidity in liquid helium-3, for which he won the Nobel Prize in Physics in 2003. Since 1983, he holds the prestigious MacArthur Chair at the University of Illinois, and he have won many important prizes during his career, including the Fritz London Prize in 1981, the Wolf Prize in Physics in 2003, and he has been knighted by Queen Elizabeth II in 2004 for services to physics. So today, he will present to us his first lecture titled Exotic Firm Superfluids and Superconductors. So thank you very much, Professor Leggett, for being with us today. And we have people here in presence, in the audience, and also people watching you from YouTube. So after your lesson, we will open to questions from the audience and also from the YouTube channel. Okay? So thank you very much, and you feel free to start whenever you want. Thank you.
Okay. Thank you. Well, thank you all for coming. What I would like to do in this lecture is to tell you a little about some of the properties of both superconductors and neutral Fermi systems, which form Cooper pairs, which are different from the original simple BCS, Bodine-Cooper-Schrieffer picture. So this will not be a complete story by any means, but I thought you might like to know about some of the rather amusing things one can do with these systems. So my first lecture is about superfluid helium-3. Next slide, please. Thank you. Helium is actually the simplest element in the periodic table. Electronically, it's a rare gas. It's completely inert. Helium-3 is, if you like, the simplest isotope of helium. It's simplest in the sense that unlike its slightly heavier cousin, helium-4, it doesn't even form diatomic molecules in free space. But it does have a nuclear spin of half, and that makes it particularly interesting. And in fact, helium-3 probably has more different uses than any other isotope in the periodic table. In the gas phase, it's used for the NMI imaging of people's lungs, particularly important these days, of course, of COVID. It's used for particle detectors. In the solid phase, we can study the motion of thermal vacancies. We can use it for differential cooling. And it does undergo a rather interesting nuclear magnetic phase transition. That's really a whole subject in itself, and I won't try to talk about it today. What this talk is about is the liquid phase of helium-3. That was actually realized in bulk pretty much 70 years ago now, actually more. And since 1972, 50 years, it's been known that it can actually become superfluid. So roughly speaking, what I'm going to do in this talk is first I will give you some brief reminders about Cooper pairing in classic superconductors, by which I mean superconductors like, say, aluminum or tin or lead. In other words, simple BCS theory. Then I will talk about the different form of Cooper pairing, which occurs in superfluid helium-3. And then finally, I'll talk about some idiosyncrasies of uniform superfluid helium-3. And I will particularly stress the notion of superfluid amplification, which I will explain in a few moments. So next slide, please. Thank you. So let's first just review a little material about the BCS theory of superconductivity in metals. Well, the electrons in metals are fermions of spin 1/2. The Fermi temperature is typically something like 10,000 degrees Kelvin, whereas the transition temperature for most of the so-called classic superconductors, aluminum, tin, lead, whatever, that's about 10 K. So the ratio of the superconducting critical temperature to the Fermi temperature is very small, something like 10 to the minus 3. So that means that already by the time you get down to the temperature of onset of superconductivity, the electrons are already very fairly degenerate. And so that means that in the normal state, above the transition temperature, that is in principle described by the Fermi liquid theory developed by Lev Landau. However, the Fermi liquid effects are often in the traditional superconductors, they're pretty small, and generally speaking, they're rather difficult to see. So for most practical purposes, you can regard the normal state of metals like aluminum or tin or lead as pretty much a free degenerate Fermi gas. And that indeed is what BCS did. They modeled the normal state as a weakly interacting gas with, however, a weak fixed attractive interaction. That's their picture. So what happens when the metal becomes superconducting? Well, basically what happens is that Cooper pairs form. So what does that mean exactly? Well, technically what it means, and this is something which was pointed out very nicely by C.N. Yang soon after the BCS theory, technically the difference between the superconducting state and the normal state is that in the superconducting state, the so-called two-particle density matrix has a single macroscopic eigenvalue with an associated eigenfunction. Well, that's a rather technical language. What I think most people would prefer to say is that you get a sort of diatomic quasi-molecules, basically a set of pairs of electrons are formed, which crucially are all doing the same thing. So they're all described by the same molecular wave function. And this quantity f, which technically is the single eigenfunction of the two-particle density matrix, which corresponds to a macroscopic eigenvalue, you can think of this as just the wave function of the Cooper pairs. And another language for it, if you like, is as this so-called anomalous average, which is the formula down at the bottom of the screen. So let's just think of what's happening as the following. The electrons form diatomic or really dielectronic molecules, and then those molecules undergo Bose condensation. In other words, you have a macroscopic number of pairs of atoms all doing the same thing at the same time. And that is the phenomenon which I will describe as superfluid amplification. Now, can we go to the next slide, please? I think there's a rather nice picture of this. Yes, here we are. This picture actually was not of the electron pairs in superconductors. It's actually of the pairs of atoms in a Bose condensate formed in a cold atomic gas. That was first done in 1996. Science magazine always declares at the end of the year what they call a molecule of the year. And in 1990, I think 96, might be 95, anyway, they declared it to be the Bose-Einstein condensate. So in a Bose-Einstein condensate, you have all these guys in blue. They are all identically dressed, and they're all doing exactly the same thing at the same time. And then you have a few other guys who are dressed differently, and they're all just running about doing their own thing. But let's focus on the Bose condensate. So remember, the important thing, all the atoms, or in the case of superconductors, all the Cooper pairs, are doing exactly the same thing at the same time. And now let's see what kind of consequences that has. Next slide, please. Okay. Well, before we do that, let's just look at the structure of the wave function of the Cooper pairs in a superconductor. And here I'm just discussing the original BCS theory of superconductivity. I'm assuming that the center of mass of my dielectronic molecule is fixed, and moreover that the spins of the electrons involved are fixed. So then the wave function of the Cooper pairs can just be expressed as a function of the relative coordinate. And in the BCS theory, it's only a function of the magnitude of the relative coordinate, not of the direction. So, I don't know if you can see me, but if you like, you have pairs which are rotating around one another, but they all look exactly the same from any possible direction. And now if we look at this wave function a little more in slightly more detail, we find that it has that form in the first equation on this slide, where the quantity capital E sub k is the well-known square root of little ek squared plus delta squared, where little ek is the kinetic energy relative to the Fermi surface, and delta is the famous BCS energy gap. And now if you actually work out, do a bit of algebra, and work out what that function f of r looks like, then crudely speaking, for most of its, most values of r, it looks like that second equation on the slide. It has some prefactor, which we're not for the moment terribly interested in. Then it has this factor sine kfr divided by kfr. Well, now what is that? that is simply the relative wave function of two free electrons at the Fermi surface. So you can imagine they just come in and go out. They don't really interact with one another appreciably. That's their relative wave function. So if that were all, then it wouldn't be particularly interesting. I'll just say, well, we just have these pairs of electrons which are just doing what they like to do in the normal phase. But then there's this factor which I put in red here, exponential minus r divided by xi, and the quantity xi can be regarded as the radius of the pair, because what happens is that if I plot out, now I go down for a moment to the figure in blue at the bottom of the slide. If I plot out this wave function, what does it look like? Well, if the distance is short compared to that characteristic length psi, then, as I say, the wave function just looks like the wave function of two freely moving electrons in free space. But if I go further than psi, then gradually the wave function will tail off and go to zero. In other words, I really do have a bound state of the two electrons, even though at first sight it looks as if they're not bound at all. You have to go to a distance of the order of xi to figure out that they really are bound. Now, it turns out in BCS theory, this pair radius, apart from a factor of order 1, is h bar, Dirac's constant, times the Fermi velocity, E sub f, divided by the energy gap. And because the energy gap is very small compared to the Fermi energy, that means that xi, the pair radius, is very large compared to the Fermi wave vector, or equivalently the inverse Fermi wave vector, equivalently the distance between electrons. Incidentally, I've just put a little red question exclamation mark for the very short distance part of the wave function. No one ever discusses that. I don't know a single textbook in which the behavior there is discussed, but in fact, it must be rather interesting because, after all, remember, no matter what is the interaction which binds the pairs, and that's because the subject in its own right, you do know that at short distances, they are strongly repelled from one another by the Coulomb interaction. And so the pair wave function really has to take that into account. Luckily, however, that only affects the behavior at very short distances, typically of the order of the Bohr radius or less. So people usually forget about anything that goes on there. Anyway, so that's crudely speaking what the wave function looks like in a typical BCS superconductor. Okay, next slide, please. One more thing to notice is that if I define my function f as I did on the last slide, and I take its square and integrate that over R, over space, then what I find after a bit of algebra is that it comes out to be the total number of particles involved multiplied by delta divided by the Fermi energy, and let's say that's usually pretty small. Remember that delta, the energy gap, is about the same in energy units as the critical temperature. And so that factor is something like 10 to the minus 4. And so you can regard this integral as effectively the number of Cooper pairs. And we see then, if we define it in this way, we see that the number of Cooper pairs is very much less than the total number of particles. That's very different from what happens when helium-4 goes superfluid. When helium-4 goes superfluid, the number of condensed single particles, single atoms in the condensate is of the order of the total number of atoms. It's thought, in fact, in helium-4 it's about 10% of it. So quite comparable to the total number. But in superconductors, the number of pairs, as I say, much smaller than the total number of atoms. Now, one final thing. In the original BCS theory of superconductivity, this relative wave function of the pairs, as we've already said, is a function only of their separation, not of the angle between them, which can be put more technically by saying that the pairs form in an orbital S wave, a relative orbital S wave. And moreover, the spin state of the pairs is a simple spin singlet. So this means that the pairs have no orientational degrees of freedom. From the point, and in fact, the relative wave function of a Cooper pair in a typical classic superconductor, like, say, aluminum or lead, is really pretty boring. It has essentially no characteristic orientational degree of freedom. And actually, it turns out, although this is not at all obvious, it turns out that that fact is actually rather important when one comes to consider the problem of the stability of supercurrents. But that, again, is a rather complicated subject I won't try to go into today. Anyway, remember that in superconductors, no orientational degrees of freedom. Okay, next slide, please. Well, historically, superfluid helium-3 was the first anisotropic Cooper-paired system discovered. The atoms of helium-3 are also fermions of spin a half. In this case, the Fermi temperature, remember the mass of a helium-3 atom is much greater than the mass of an electron by a factor of the order of 1,000. So that means that the Fermi temperature for helium-3 is about 1 degree Kelvin. The temperature for the onset of the superfluid phase experimentally is about 10 to the minus 3 degrees absolute. So again, just as in superconductors, the ratio of T sub C to T sub F is again about 10 to the minus 3. So again, that means that the helium-3 atoms are strongly degenerate at the onset of superfluidity. However, there's an important difference from electrons in the normal phase of a superconductor. Remember that the normal phase of a superconductor is pretty much like a non-interacting Fermi gas. But in the case of the helium-3 atoms, you really can't neglect the interactions at all. And so it turns out that the low-lying states, including the states of the superfluid phase, must be described not in terms of simple free helium-3 atoms, but rather in terms of so-called Landau quasiparticles. A Landau quasiparticle, you can think of that as something like a single atom accompanied by a sort of screening cloud of other atoms which go with it. And what this means is that in the normal phase of helium-3, Fermi liquid effects are actually very important. So that quantitatively, the properties of normal liquid helium-3 are really rather different from those of a non-interacting gas. And this has been known for many years before the discovery of superfluidity. Well, again, as I say, the system is, when it goes superfluid, the system forms Cooper pairs. Again, we find that the before I go on, let me just take a brief look at the phase diagram, which is the diagram on the right of this slide. You see that at high pressures, the system is solid, and we're not particularly interested in that. At lower pressures but higher temperatures, you have the normal phase, which I've just talked about. And then actually, we have not one but two superfluid phases, traditionally called the A phase and the B phase. And all of this is going on at a very low temperature, about 3 milledegrees absolute. So again, how do we understand what's happening? Well, following Yang, we believe that the two-particle density matrix, rho sub 2, it still has one and only one macroscopic eigenvalue. And you can still define a pair wave function corresponding to that eigenvalue. However, even if the wave function of the Cooper pair does not depend on the center of mass, nevertheless, it still has orientational degrees of freedom. In other words, it depends non-trivially on not only, in fact, the relative coordinate of the two atoms involved, but also their spins. And this is the qualitative, the most important qualitative difference from the Cooper pairs which form in superconductors. Well, I say that has different orientational degrees of freedom. So what do we think these are? Well, there's a standard identification of both the A and the B phases, which I think most people now are basically pretty happy about. In both the A and B phases, the Cooper pairs not only have total spin 1, in other words, the spins are parallel rather than antiparallel as they were for BCS, but they also have relative orbital angular momentum equal to 1. But actually, that still leaves quite a lot of possibilities. Next slide, please. Yeah. So the general belief is that the wave function, or the Cooper pair wave function, in the A phase, well, there are various ways of representing it depending on how you choose your axes. But let's suppose that we choose our spin axis in a particular way. Then we can take the spin part of the Cooper pair wave function to have this this form represented in the first equation of this slide. And you notice that you have a plus sign between the two terms up 1, down 2, and up, down 1, up 2. And that's different from what occurred in a BCS superconductor where you had a minus sign. And that's a very important difference. And you can write it this way if you choose your characteristic spin axis in a certain way. If you choose your spin axis differently, then you have a different looking form of the spin wave function, but it really is the same one, it's just written with respect to different axes. In any case, the wave function is a product of spin and space terms. What about the space part? Well, the space part in the A phase is rather interesting. It has a part which depends only on the magnitude of the relative coordinate, and that's rather boring by and large. But then it has a very interesting dependence on the relative angle of the two atoms forming the pair. If I choose my axis, my space axes appropriately, then we find that the wave function has the form of sine theta exponential I phi, where theta and phi are the usual azimuthal and polar angles. Now, if we're actually talking about a diatomic molecule, then what that kind of wave function would correspond to is an angular momentum of h bar, h over 2 pi, per pair. And so you might say to yourself, well, the Cooper pairs then must have this angular momentum, h bar per pair. And believe it or not, although the subject of superfluid helium-3 is 50 years old this year, people still can't really agree whether that answer is right or not. Luckily, it turns out not too much depends on whether you believe that statement or not. You can still, even if you don't know the answer to that question, you can still calculate most of the properties of the system. And indeed, it turns out that the properties are, for the A phase, anisotropic, separately in spin space and orbital space. For example, if we look at orbital space, then the energy gap as a function of the direction on the Fermi surface has this form, the last line on this slide, which means that the energy gap actually goes to 0 at the points plus or minus L, at the so-called poles. And that's very important because it means you can get a lot of excitations near those points. Next slide, please. the B phase is actually even more interesting. Turns out that for any particular direction on the Fermi surface, whether it's in real space or in K-space, you can always choose these spin axes to be of that form which we had for the A phase. But the characteristic axis that you have to define is different for different points on the Fermi surface. Now, when this B phase was first thought of, which actually it actually was first thought of not by Balian and Wertheimer, who tend to get their names attached to it in the Western literature. It was actually first thought of by someone called Yuri Dovin in the former Soviet Union. And he wasn't actually even a condensed matter physicist. He was a laser physicist. But nevertheless, he was the first to think of this state. And when he thought of it, and when Balian and Wertheimer, who rediscovered it independently, when they thought of it, they assumed that the d vector, the characteristic spin vector, had to be just the same as the direction on the Fermi surface. And what that would mean is that the spin of every pair is opposite to the orbital angular momentum of that pair. And so in the language of diatomic molecules, that would be a so-called 3p0 state. And that would be totally isotropic and actually rather boring. But luckily, life is a little more interesting than that. It turns out that in real life, the B phase is the phase that you get by starting off from that boring 3p0 state. But then, because of the dipole force, you have to rotate the spins relative to the orbital coordinates by this funny angle 104 degrees, which is actually the inverse cosine of -1/4. And the argument for that is straightforward, but it's a little too long to give you. Now, that's very interesting because you haven't said whether you rotate clockwise or anti-clockwise. And so you have to do one or the other, and that then breaks the orbital parity or the inversion symmetry. However, it does not violate time reversal. So that's a really rather amusing case, which is not too common. So this Balian, this B phase has the characteristic that the orbital behavior by itself is isotropic, the spin behavior by itself is isotropic, but the properties involving spin-orbit correlations, if there are any, are anisotropic. And let's just look at that a little further. Next slide, please. Okay. Yeah, just let me give you a feeling of this by a picture. If you start with normal helium-3, then and you think about a particular pair of atoms, then they have a given total spin, which is the red arrow, and they have a given orbital angular momentum, which is the green arrow. And in the normal phase, the spin orientation is random, the orbital orientation is random, and the orientation of the spin relative to the orbital angular momentum is random. Now, in the A phase, what happens is that now things are not so random. The spin of a pair of atoms, which are forming a Cooper pair, that always is oriented up or down along a particular axis. That's the diagram on the left here. The orbital angular momentum is actually oriented perpendicular to that. So that's the green arrow there. So that means that the expectation value of the spin itself is 0 because there's many ups and there's downs. But the expectation value of S squared is not 0. And the orbital momentum, the orbital angular momentum is also not 0. In the B phase on the right, you see, now that's very interesting, you see, in the B phase, because what you see is that the red arrows are still oriented at random. The green arrows are still oriented at random. But what is not random is the angle between the red arrow and the green angle. If you look at that diagram closely, you'll see that angle is always the same. It's actually that funny 104 degrees. So this means that the expectation value of the total spin is 0. Total value, expectation value of the orbital angular momentum is 0. But there is nevertheless a characteristic vector, which is not 0. It is the cross product of L and S. And that would be out of the screen in this diagram, pointing out of the screen. Now, why did all this happen? Well, basically it happens because of the dipole energy that depends on the relative angle of the red and green arrows, and that then so determines their orientation relative to one another in both the A and B phases. Next slide, please. Yeah. Well, okay. So this is what theorists think about superfluid helium-3. But how might we try to see that? And in particular, how might we see the exotic nature of the pairing? Well, there are lots of ways of doing this, but one example which I rather like is how would you see the spontaneous violation of P and T symmetry in the A phase? Well, it's a very nice experiment done by Ikegami and his group in Tokyo a few years ago, which tries to do just this. And what they do is to take a cell full of liquid helium-3, and they put a couple of electrodes in it, and they apply a voltage so as to pull electrons off one electrode and to drive them to the other electrode. And they actually, and you see that the current leads are actually oriented perpendicular to the voltage leads. So it's a bit like the quantum Hall effect, where the system is very different. And what they do is to plot the difference between the current in the upper lead, upper current lead, and the lower current lead, I1 minus I2. And in the normal phase, that's extremely boring. There is no difference. In other words, current flows equally into the upper and lower leads. Similarly in the B phase, nothing interesting. However, in the A phase, I should label this better, but the second diagram down on the right of this slide is actually for the A phase. And what you see there is that as a function of T, you do temperature, you do get a difference between I1 and I2. And it actually changes sign, although that's not a terribly important point to notice. But how does this work? Well, basically, there is an intrinsic Magnus force on the electron as it passes through the liquid. And this Magnus force is proportional to that vector L, which was the effective relative angular momentum of the Cooper pairs. If the L vector is pointing into the screen, then the electron will be deflected rightwards, and it will go into the upper lead, or preferentially go into the upper lead. If the L vector is directed out of the screen, then it'll be deflected in the opposite direction. It turns out that you, in zero external magnetic field, you apparently get this happening at random. So in other words, for one run, the picture will be one type of curve, and for the next run, it might be a different one. And so this will happen more or less at random. However, what's really quite unexpected, or at least was at first, I think, to experimentalists, was that a magnetic field appears to be able to affect this behavior. In other words, it can orient the L vector to be in or out. And that then indicates the coupling, that there must be a non-zero energy coupling the L vector to the magnetic field. And that in turn means that helium-3 must be a weak orbital ferromagnet with a magnetic moment along either plus or minus L. We don't actually know which, but it must be one or the other. That's very puzzling. Helium-3 atoms are neutral. So how on earth could that give rise to a magnetic moment? Well, let's go to the next slide, please. Okay. Well, there is, in fact, a known effect in chemical physics, and this was actually first realized and analyzed by Giancarlo Wick, who is actually much better known for Wick's theorem, but he actually wrote this paper way back in 1948, analyzing this effect. It turns out that the rotation even of homonuclear diatomic molecules can give rise to a magnetic moment. Why? Well, I mean, if the atoms are not polarized in any way, then the magnetic moment has to be zero. There's just no way in which you can get a circulating current out of this. But let's suppose that you consider the possible polarization of the atoms by one another in the diatomic molecule. Well, it turns out that if you just consider Coulomb and van der Waals forces, you don't get anything interesting. But if you consider genuine chemical effects, that is, effects which genuinely depend in detail on the quantum mechanical orbitals, then you find there is a tiny polarization. Charge will be slightly polarized towards the center of the molecule. And now you see, if you rotate the molecule in that state, you will in fact get a finite magnetic moment. Now, as I say, that effect's been known in chemical physics for 80 years. But even in covalent homonuclear diatomic molecules like the carbon and standard carbon molecule, it's a very tiny effect. And moreover, it falls off exponentially with the radial distance of the two atoms from one another. How can that work for helium-3? In free space, two helium-3 atoms don't even form a balance state. Now, for Cooper pairs, of course, they do form a balance state, but the vast bulk of the probability lies at a distance which is way, way outside the typical distance, say 2 or 3 angstroms of other diatomic molecules. So if you just were to try to calculate the magnetic moment, which would occur in this way for a single Cooper pair, it would be something like 10 to the minus 11 of a Bohr magneton, unmeasurably small. And certainly in the normal phase, we expect it to be completely unobservable. But what actually saves us now is the principle of superfluid amplification. All the Cooper pairs have to do exactly the same thing at the same time. And in other words, you multiply that factor of 10 to the minus 11 Bohr magnetons by something like 10 to the 23, and it looks as if it might just be measurable. And in fact, it turns out that it's equivalent to a field of the order of 10 or 20 milligauss, which is not impossible. And way back, in fact, this is way back in the 70s, John Wheatley's group, Paulson et al., did find some circumstantial evidence for that field, but I think that the more recent Ikegami experiments are much better evidence for it. Let me finish off by talking about what would be, if we could observe it, an even more spectacular effect. Next slide, please. Yes, I do need to talk just a little about the NMR, which is a much more easily observable effect. You remember that the dipole energy depends on the angle between the red and green arrows, the spin and orbital angular momentum. And it turns out that if you write down an equation of motion for the total spin, it has the usual normal term, S cross H0, the external field. Then there's a term which is related to the dependence of the dipole energy on the rotation around the direction of the RF field. Now, typically, in an NMR experiment, you have the situation indicated by the blue arrow on the right. In other words, the RF field is perpendicular to the static field. And that's a standard NMR experiment. However, you can also imagine an experiment in which the RF field is parallel to the external field. That's so-called longitudinal resonance. In any case, for the A phase, the dipole energy locks D parallel to L in equilibrium, and usually D perpendicular to H. And so in both transverse and longitudinal resonance, the fields move the D vector away from their equilibrium orientation, and so that gives you a shift in the transverse frequency and also a longitudinal resonance. I won't go into the theory of that. It's a little more too complicated to do so at the time available, but you can do the calculation for that, and indeed it does seem to work out. For the B phase, you find that in transverse resonance, the rotation around the RF field is equivalent to a rotation of the spin orbit angle, the spin orbit axis with the angle unchanged. That doesn't give you, to lowest order, a dipole torque. So you don't find any resonance shift in the transverse resonance. In the longitudinal resonance, a small rotation changes theta away from theta 0, and now you find a finite frequency resonance along the external field. This, as a matter of fact, this behavior was known in a rather different system, that is antiferromagnets, for quite some time. But as far as I know, it's the first time it's ever been seen in a liquid. And yes, so you can do the theory of this in some detail, and it does seem to work out. The experimentally observed resonances do agree with the theoretical predictions. So again, that's a case where you're exploiting the fact that the possibly this is on the next slide. So let me just go to the next slide for a moment. Yeah, okay, no, it isn't. But as I say, you can do the theory, so it does come out right. This is my last slide, and this is a proposed example of superfluid amplification. It concerns the possible effects of the part of the neutral current of weak interaction. This is something well known to particle physicists. There's a part of the weak interaction which violates parity but does not violate time reversal. Question, could you see this for a single particle? Answer, no, because any electric dipole moment must be of the form of the D is constant J, that's the Eckert theorem. That violates time reversal as well as parity. For helium-3b, however, you can form a quantity which violates P but not T, and that's this constant L cross S quantity. And so you could have an electric dipole moment in helium-3b which is along this characteristic spin-orbit rotation axis. And you can try to do the calculation. It involves a lot of factors similar to the A-phase paramagnetism, even more exotic chemical physics. Again, once more, the effect is tiny for a single pair. Since all the pairs have the same value of L cross S, it's multiplied by a factor of the order of 10 to the, it should be a 10 to the plus 23 actually. And so in principle, you could have a macroscopic electric dipole moment along the omega vector. That would be, I think that would be really very amusing if you've got it. It would be a macroscopic effect of the weakened parity violation due to the weak interaction. And one or two groups are actually seriously thinking of trying to set up this experiment right now. So maybe, I think I'm going to be pessimistic, maybe in 10 or 20 years' time, we might be able to see this effect. But as I say, that would really be, I think, pretty spectacular. But let me just sort of sum up by saying that essentially all of these really exotic effects that you find in superfluid helium-3 are a result of this factor of superfluid amplification. simply the fact that all the group of pairs are doing exactly the same thing at the same time. Well, I suspect I might have gone way over my time, so let me stop at this point and thank you for your attention. Thank you. 9. Okay, that's the end. Hello, can you hear me?
Are you listening? Yeah?
Yeah.
Yes? Okay. So nice. Thank you very much for the lecture, Professor. So I will open for questions. So does anyone have a question in the audience? Yes? You can come.
Hi, Professor.
Yeah.
My name is Márcio. Thank you very much for this enlightening lecture, for all the explaining BCS theory and the Ilium trace. I understood the difference between Cooper pair in superconductor and the Ilium tree is lattice vibration and the fluctuation spin, okay?
I'm sorry, I didn't catch the word you used. You said it's spatial?
The mechanism, the superconductor lattice vibration and the Ilium trees fluctuation spins.
Oh, okay. Well, yes, this is certainly a very popular theory. Yes.
I would like now what's mechanism of superconductor couplates a mystery, the two mechanisms.
Oh, okay. Yeah. So if I understand you right, you're reminding us that in a standard old-fashioned superconductor like, say, aluminum or lead, the mechanism of formation of Cooper pairs, which I haven't actually talked about in this talk, is due to exchange of virtual phonons. But in helium-3, it's usually thought to be due to exchange of spin fluctuations. And then you ask, well, what about the high temperature cuprate superconductors? Well, no one is really sure. It's still quite controversial, but yes, there is a group of people who certainly think that the mechanism is exchange of spin fluctuations. That's certainly one quite popular theory. But there are other people who really think of it in a rather different way. They, for example, think that in some sense the main effect is the very, very hardcore Coulomb interaction, and that this gives rise to certain very exotic kinds of pairing mechanism. It really isn't entirely clear to me that these are qualitatively different theories. I suspect we may find at the end of the day that these are really different ways of representing what is essentially the same physical idea. But right now, I just have to say the subject is very controversial.
Okay, thank you.
Did I answer your question?
Thank you. There is another question. Yeah, Vanderlei?
Oh, hi, Professor Leggett. Thank you very much for the nice lecture. And we appreciate that you accept to talk to us and give us so enlightening lecture. I have two questions, and a kind of comment. The first one is during your presentation, you showed to us that the Cooper pair has a kind of radius, and you gave the number 10 to the 4 angstrom, if I could read correctly the transparency.
Yeah. Yes,
okay.
Yes.
Now the question is, if I make a droplet of helium-3 that has a radius less than this characteristic Cooper pair, am I going to suppress the superfluidity of that droplet because of the size?
That's a very interesting question. If you were to ask the same question for a standard superconductor, then, in other words, if you would ask the question, if I have, say, a metallic grain, which has a size less than the Cooper pair radius, would I still get superconductivity? Then I think we have an experimental answer to that question, and it is yes. Yes, we would. However, it's generally believed that any kind of scattering, impurity scattering or anything else, which gives you a mean-free path, small compared to the pair radius, will destroy anisotropic superfluidity, that is the kind of superfluidity or the kind of Cooper pairing which occurs in helium-3. The experimental evidence on this, I think one has to say, right, as far as I know, I may not have kept up with all the most recent experiments, but as far as I know, experiments really have not been quite able to resolve that question. The evidence does seem to be, on the whole, that if I have, for example, a helium-3 film, which is thin compared to the pair radius, then I probably do destroy superfluidity. But these are very difficult experiments, and I think one can't be absolutely sure of the answer.
Okay.
Can I answer your question?
I have another question. It's concerning the tiny magnetic momentum of the pairs when you induce. That means that if I superimpose a magnetic field in helium-3, I'm going to have a kind of anisotropic superfluidity?
Yeah, well, yes. Yeah, I mean, the thing is, even without a magnetic field, typically the liquid will be anisotropic because of the effects of boundaries and so forth. So the L vector, the vector of the apparent relative orbital angular momentum, that usually does have a definite direction, a definite orientation over most of the cell. And so yes, and that does mean that the properties are anisotropic, and that's been, for example, found in ultrasound absorption and other experiments. But if you now impose a magnetic field, this is a different orientational mechanism, and so it'll compete with the boundaries and so on.
Okay, thank you. Now it's just I would like to hear your comment because you know, when I was a young kid, superconductivity and superfluidity were in different parts of physics. We treat them differently, and nowadays with the help of cold atoms and the high correlated system and everything, we learned that those phenomena are the same, and that modify the way we look into those super properties. So I would like to hear from you a comment about this evolution, that now we understand that they both are the same phenomena that we treat with the same tools. Thank you.
Yeah, okay, thank you. As a matter of fact, rather soon after the BCS theory of superconductivity, C.N. Yang did effectively write a paper which claimed that superconductivity and superfluidity were essentially the same thing. However, the only difference in those days was that superfluidity, there weren't too many systems known. The only neutral superfluid system known was, in those days, helium-4, and that is, of course, superfluidity of single atoms, since it's a Bose system. And the only type of superconductors known were the classical variety, in which the superconductivity is certainly due to Cooper pairs. But Yang pointed out that despite this, they were really much the same phenomenon. However, I think people really only became convinced this is right, as you mentioned, once one had the ultra-cold atom system, and one could actually tune the parameters so that you go continuously from what looks like a Bose condensate of diatomic molecules all the way through to a set of Cooper pairs. I mean, I think that the ability to tune in this way so as to affect the so-called, what we call the BC-BCS crossover, I mean, I think that really has established in people's minds that Yang was right, and that his approach is the best way to look at things.
Thank you, Professor. One last question? No? Yes? So one last question. Wait a minute.
Thank you, Dr. Leggett, for the wonderful lecture. My question is about the anisotropy of the possibility of the anisotropy of the Cooper pairs. Is it possible to conceive a situation where you give some angular momentum to your Cooper pair and it gets picked up just by one of the electrons? Let's say the spin down just sits there and all momentum goes to the spin up component?
That's an interesting question. I think probably the answer is, in principle, you could write down a possible state of the system where this was happening. But in practice, what you'd find is that the energy of that state is much greater than the energy necessary to drive the system normal. So that if you really tried to do this in real life, the superconductivity would just be destroyed, I suspect. It's an interesting point. I mean, it's conceivable that even if not for electrons, maybe for certain kinds of atom in an ultra-cold Fermi gas, this might be possible. I don't think anyone, to be honest, I don't know of anyone who's really thought seriously about that question, but it's worth thinking about.
Thanks for your answer.
Okay, so if we have another question, we can do it tomorrow on his second lecture. So let's thank Professor Leggett once again. Thank you very much, Professor, and we see you tomorrow. Thank you.
Okay, thank you.
Bye.
Bye-bye.
Okay. Okay, so poster section with Monica. Ciao. We see you tomorrow.
Hello, everyone. We'll start now your poster section. As before, we start calling the on-site participants. Please, Larissa Nolasco. Larissa, you present the poster with the title Semi-Classical Investigation of Magnetic Optical Trap with Reduced Number of Light Beams. Larissa, please. Larissa, o seu pôster tem o PDF também. Se você quiser apresentar o pôster, né? Pode ser só as perguntas mesmo. Que página que você está, Larissa? Você lembra? Vamos lá. Se você quiser alguma coisa em detalhes, tem o PDF.
Hi, everyone. I'm Larissa, and I am an undergrad student here at IFISC. So my poster is about a semi-classical investigation of a magneto-optical trap with a reduced number of light beams. And basically, what we did was to study the forces acting on different configurations of traps to see if they could work. And about that, I received 3 comments. The first one is from Abel, and his first question is about the size of the cloud. He was concerned about rescattering. So to estimate the cloud size, we used a thermodynamic approximation that is a lower limit approximation to the cloud size, because it do not consider interaction between the atoms or rescattering. So the plot we showed is just a lower limit approximation of the cloud size. Then he asked about capture velocity and the predicted steady state atom number. In this first analysis, we are concerned about the trap already in equilibrium conditions. So we do not study yet the loading process of the mod and the efficiency of these traps. So I can answer the question, but it's something that we should study. The next comment is from Pedro. Pedro asked about the equilibrium position and how it changes with the angle of the beams. So the equilibrium points are the points where the radiation pressure force counterbalance the gravity force. So if we change the angle of the beams, it would affect the force, the light force, so the equilibrium position would change. The next comment is from Bruno. His first question was also about the cloud size, but he wanted to know how it varies with the tuning. So in the direction along gravity, the cloud size tends to be very small because the atoms accumulate in the equilibrium position. But in the plane perpendicular to gravity, the atoms spread in the region between the peaks of the force. So in that region, changes if we change the detuning. His second question was about the operating limit of the traps. And we do have an upper limit to the tuning because we need to, the light still needs to be in resonance with the transition frequency, but we didn't map that. And the last question was about temperature. So if we assume the same parameters that what he asked about, I believe these few beams configurations could reach lower temperatures because it uses less laser beams. But that's just a guess. We didn't actually do the calculations for this. And that was all. Anybody has any questions? It uses less space in the lab, so we can prepare another experiment close to it, and we have more space to do it. Yeah, the equilibrium points are below the zero of the magnetic field, so we have spin polarized atoms that could be interesting, and we could probably reach lower temperatures. So it's a nice thing to study, I guess. Any more questions?
Thank you, Larissa. Our next participant is Marcia Fernandez, with the poster Coherent Light Matter Interactions in Dense Atomic Clouds.
Hello? Are you listening? Okay. Okay, my name is Marcia. I'm a PhD student from here, the Physics Institute of San Carlos. And I'm going to present a poster titled Coherent Light Matter Interaction in Dense Atomic Samples. And basically, the main objective of this research is to study a particular case of light-matter interaction, that is the light scattering in dense atomic samples. And this is important for applications like in quantum technology or even biology. And even when most systems are in the dense regime, this regime has been little studied. And the experimental results, they present a difference with relating to the existing theoretical models. And that's why we are interested in studying this kind of systems to understand a little more this physics, right? So the theoretical model that is usually used to study this system is the coupled dipole model, which basically the time evolution of the atomic operator in the Heisenberg representation leads to a relation between each component of each atomic dipole induced in the system. And this interaction will present long-range terms and short-range terms that are very important when we study the dense regime. So experimentally, the way to obtain this dense atomic sample is to transferring the atoms for a magneto-optical trap to an optical dipole trap. And the beams are created in order to obtain a specific geometry and a specific density of this sample. Once in the dense regime, the first experiment will be measuring the coherent transmission of a near resonant light from the sample. And the results we have until now is that we obtain the cloud, and we're making a few characterizations. And as part of the characterization, we made the frequency oscillation of this cloud. And we also made some simulations based on the coupled dipole model to observe the behavior of the curves of coherent transmission. And we obtained a few curves that it should be the behavior of the future results, experimental results. So I'm going to pass to the questions now. I have 3 questions here. It's more than 3. Wait. Arnold asked why the geometry is different in the simulations. Okay. This is an important question, actually, because in the experiment we have a Gaussian cloud, but we have a limitation on the simulation of the number of atoms we can simulate. So basically, what we consider here was a Gaussian distribution in the longitudinal direction, but in the transverse direction, we consider an uniform distribution that it will be the experimental case of a beam very small with compared with the size of the sample, right? So in this situation, we just are simulating the atoms that are actually interacting with the light. The other question was, he's talking to, talk a little more about the phase contrast imaging. I think I didn't talk about it right now in the presentation, but okay. Basically, as part of the characterization of the cloud, we are trying to implement phase contrast imaging. And this is because the absorption imaging, that is the technique we use to observe the cloud, that, for example, those images, this technique has limitations to observe dense clouds. And we're trying to obtain a high-density cloud, right? So this technique, basically, we don't construct the shadow of the cloud like in absorption imaging, but we observe the global phase of a beam that interacts with the cloud. And this technique is off-of resonant, so it is not a destructive technique like absorption imaging. And to create those imaging, we need to use a phase mask in order to create a phase shift between the light that interacts with the atoms and the light that doesn't interact with the atoms. And we are doing this phase mask using a spatial light modulator in our system, right? So I have more questions here. Bruno asked, is the coupled dipole model simulation a quantum Monte Carlo simulation? Okay, the answer is no. First of all, I'm not doing quantum simulations here. I'm considering a classical model. And also, okay, the model basically, what we have is a matrix that contains all the interaction terms between the dipoles of the system. And what we do is a diagonalization of this matrix. That's basically what the simulation does in order to obtain an exact result. So the other question is related with the other one, so I'm going to pass to the last question that is from Dalila. What do the colors of the curves represent in the first imaging? Okay, here. Basically, those images are curved for different density, atomic density. We're passing from the dilute regime, that is the green curve, to the high density regime, that is the blue one. It's basically that. I don't remember exactly the values of the densities. And the last question from Dalila is, in the proposal of coherent transmission, you have an schematic with, okay, it's a blue laser, and yeah. She's asking if this can be done using the red transition. And well, we need a transition of the kind J0 to 1, okay, total angular momentum 0 from 1. And in a strontium, we actually have these two options, the blue transition and the red one. But the red transition is very narrow. So first of all, we have a very low scattering rate. So the signal we're going to observe is going to be very, very low. It's almost impossible. And also for this measurement, we need a low intensity beam. I mean, a beam with an intensity under the saturation intensity. And as the red transition is so narrow, the saturation intensity is too small. So we can basically do that experimentally. So this is all. Any other question?
Thank you, Marcia. I would like to invite now Matheus Mota, who is the poster conversion of paraxial modes in third-order nonlinear media. Está pertinho aqui, Matheus.
So, hello everyone. My name is Matheus, and I'm a PhD student at Federal University of Pernambuco in Recife. And so I'm going to try to be quick on the overview. This work focuses on the theory of the transfer of optical mode structure in a four-wave mixing process that takes place in a rubidium vapor cell. I have a nice picture here that illustrates the main idea. We have pump beams that we can control their shape, and we are going to be interested in the blue generated field. I'm going to the comments, the questions from Dalila. These were very good questions. Thank you. And the first one is, what's the calculated efficiency of the conversion? Actually, in our model, we don't look in detail at the power conversion efficiency, but we are very confident that, this system is very common, and we are confident that we can achieve good conversion. But this is a very good question, especially because we are working with highly non-uniform beams. These are not Gaussian beams, so it's really important. And by the way, my advisor just sent me quantitative data to answer you later. But the second one is there any combination of Hermite Gaussian modes for the pumps that generate a pure Gaussian mode? And I have not thought of this, but I believe a good answer is if we convert the basis from the Hermite Gaussian basis to the Laguerre Gaussian basis, we can put opposite angular momenta in one of the pumps, the two pumps, like +1 or -1, and then they will sort of cancel out. But I think we still don't get a pure Gaussian mode, 0-0 mode. And what do you expect to change if the medium has a higher density, an atomic beam or a magneto-optical trap? So also another good question, but regarding the density, I believe it will affect mainly the power conversion efficiency of the process. But one thing that I find that to be more important, since this was actually the theme of my master's thesis, I worked with a magneto-optical trap, is that in the trap we have a very small cloud of atoms in comparison to the rubidium vapor cell. And so we are going to have a thin medium regime, and this completely changes the dynamics of the mode conversion. Okay, we have a very specific selection rule that is satisfied in this case because we have a thick medium, and it would not hold in the trap. So this method specifically doesn't work in a small medium. So that's basically it. I think I went too fast, but does anyone have any other questions? No? Okay. Thank you.
Now you have Michele Moreno, who is the poster characteristic length scale during the time evolution of a turbulent Bose-Einstein condensate. Michele, deixa eu te achar aqui. Começa se introduzindo, te apresentando, Michele? Ou depois vai para as perguntas.
Tá. So good afternoon, everybody. My name is Michelle, and I'm a PhD student here at the Instituto de Física de São Carlos. So the main idea of our work is to investigate the decay regime of quantum turbulence in a trapped Bose-Einstein condensate. We work experimentally with rubidium-87 atoms. So, in order to do this, we calculate and define a characteristic length scale, which is inspired from the integral length scale from the classical turbulence. So we define this characteristic length scale as an integral function of the momentum distribution. And we use the inverse Abel transform to use our 2D momentum distribution measure to calculate reconstruction in 3 dimensions. So we can try to interpret this characteristic length scale as the evolution of the length scale where most of the particles reside or are located. So I'm going to explain briefly how our experiment works. So once we have our condensate just after the evaporation process, we perform an excitation using an oscillating magnetic field, and we excitate the cloud during a certain time of about 30 milliseconds. Then we stop the excitation and let the cloud to evolve inside the harmonic trap. And then we let the cloud to expand freely, and we take absorption images like the ones you can see here. So, as I mentioned before, we calculate our characteristic length scale using the 2D momentum distribution, the projected momentum distribution we are able to measure, and the reconstruction using the inverse Abel transform. So in this plot, we present the characteristic length scale as a function as a function of time for different excitation amplitudes. So for example, we can identify more or less 3 regimes. The first one you can see here is for a small or a low excitation amplitude, so the system does not reach a perturbed, a disordered state. In the case of intermediate perturbations, we can see that this length scale starts to decay, but not as fast as it does in the case of higher amplitudes. And we can see that in this case, it faster reaches a value which corresponds to our healing length, which is about 0.15 micrometers. And we can compare our results in the reconstructed 3D momentum distribution, and we can appreciate that both have a similar behavior. We also can consider that these curves have an exponential behavior. So we can extrapolate and calculate the characteristic length just at the beginning of the excitation. And we can, in these 2 plots, can compare for the 2D and the 3D cases. We can see for the characteristic length that they have similar behavior too. For different excitation amplitudes, they all have almost the same values, but they differ in quantitatively. And we can try to explain this because in this case we are using the inversible transform, and by doing this we slightly shift the momentum distribution towards a region of higher momentum. And that's why we don't have similar values. But we can also calculate the characteristic time, and as we expected, we have similar values in both cases. So that's it. And now I'm going to answer the questions. The first one is from Dalila. She says, it's possible to see an oscillating behavior in figure 5. Okay. We can see this, maybe we can try to explain this oscillating behavior in all the curves because at the moment we take the absorption images, we perform the measurement just at the bottom of the trap. So you can see that it corresponds more or less with the time we take the pictures, and maybe that's why we have this kind of oscillations. And the second question is, can you explain a bit more on the experimental details of shaking the magnetic field? The shaking of the magnetic field, and which are the higher frequencies you can achieve with your setup? Okay, so once we have our condensate, we use two coils in anti-Helmholtz configuration to perform the excitation. But one of the coils is not perfectly aligned with our harmonic trap. It is a bit tilted, so we do this in order to get to drive the cloud to some deformations, displacement, or rotations. And that's how we perform our excitation. We use an oscillatory magnetic field. And the second question, which are the higher frequencies? Well, with our experiment, we work, in this work, we used a trap frequency of 130 hertz, but we can also get a condensate from 200 or 230 hertz in the radial frequency of the trap. And I have a last question from Nicholas. Do the scaling laws you observe for the 2D or 3D momentum distributions approach to any quantum or wave turbulence predictions? I would say that in our experiment, we are very restricted in a range of our length scales. So for example, our healing length is about 0.15 micrometers, and the maximum length, which corresponds to the size of our system, is about 40 micrometers. So we are very restricted in this range. So we are not able to say that for sure we are clearly in a specific kind of turbulence. But I didn't mention, but we also we calculate the power law, and our result of our exponent, according to some recent studies, we would say that we are near the regime of wave turbulence. So that's.
Thank you, Michele. Okay, now I would like to invite Nicholas Mueller, who is the poster Anomalous Scaling Velocity Circulation in Quantum Turbulence.
So, hi everyone. My name is Nicolas. I'm a PhD student at the Observatory of Nice in France. And I will talk a little bit about how are some statistical properties of circulation in quantum turbulence. As you know, the circulation in quantum fluids is quantized, so we are interested to see if in quantum turbulence we can reproduce some of the behavior we observe also in classical fluids. So to do this, we perform some numerical simulations of the Gross-Pitevsky equation. In particular, a generalized Gross-Pitevsky equation that includes a non-local interaction term in order to reproduce the Rotom minimum in the excitation spectrum, and also includes some beyond mean field corrections. So this is one visualization of the flow we generated in the numerical simulations with the quantum vortices. So, for example, here this is a two-dimensional cut of the vorticity field, where you can see some positive and negative vortices. And what we do is we compute the circulation around closed loops of different sizes or of different areas. And thus we can study how is the scaling of circulation. So, for example, here I show you how is the second order of circulation or the circulation variance. And we observe, and we compare also with the classical turbulence. So we observe that at small scales, the scaling laws are very different. However, at large scales, we recover a very similar behavior, a very similar scaling. And this is very surprising due to the fact that vortices in classical and quantum turbulence are very, very different. Also, what we can do, which is something that you cannot do in classical turbulence, is that you can compute the circulation based on either the area of the loop or also based on the nearest vortices. So we can count the vortices and compute the circulation. When we do this, we obtain two different behaviors. When we compute the circulation as a function of the area, we obtain some very heavy tails in the probability distributions that are a signature of intermittency, while on the other hand, we obtain a behavior that is close to self-similar behavior. So when we compute high-order we can compute, we can go a little bit beyond and compute high-order moments of the circulation. If the system is self-similar, we would expect that the scaling exponents that are lambda here, this lambda p, would go as the Kolmogorov's prediction, which is 4p/3. However, what we see in these blue dots is that they present some deviation from the solid line, which is Kolmogorov prediction. However, when we compute the circulation as a number of the vortices, we obtain a self-similar behavior consistent with the probability distributions I showed before. And finally, the other thing we can do in quantum turbulence is that we know the position and the sign of each vortex individually. So we can try to create a synthetic field based on this and randomize the sign of the vortices in a random way. When we do this, we can modify a little bit the self-similar prediction, obtaining a self-similar, but again, what we observe is that we observe a self-similar scaling and a some deviations also for when we compute the circulation for the number of the loop. I mean, as the area of the loop. So yes, basically, the main result is that the circulation in classical, the intermittency in classical and quantum turbulence is very similar. So this is the main result of the work. And I have one question. So what is the influence of the beyond mean field correction to the behavior of the velocity distribution or the vortex length configurations in your system? Okay. So this is a good question because it's something that I didn't say. In particular, as I said, yes, we use this model, this generalized model that includes a non-local interaction potential and beyond mean field corrections. The idea to do this is to avoid some instabilities that develop in the system when we do the simulations. However, at large scales, like in this case here, we observe that either for the energy spectrum or for the circulation, there are no difference in the behavior. And however, at small scales, here in this case for the circulation, there is also no difference. But for the energy spectrum, we observe that the system develop the Kelvin waves of the system are kind of triggered, and you observe a better scaling for Kelvin waves when you introduce the non-local potential. But however, for the beyond mean field corrections, the system doesn't modify a lot. So I think that's it. So if anyone has questions, yes.
Which of the two methods to calculate, so you show one with area and the other one counting vortices, which one is more accurate? Because, you know, so.
I mean, you're doing different things. When you compute the circulation using the closest vortices, you kind of relax the condition of the non-trivial spatial distribution of the vortices that you may find here. For example, you see that, yes, for example, I don't know here. You see that in some regions of a flow, you have more vortices, all of the same sign, but however here you have a less density of the vortices. And when you compute the circulation in one way or another, you relax this condition of vortex clustering in a way. So I wouldn't say that they are one of them is more precise or another, but the effects you study with one way or another are different. Okay, no more questions? Thank you.
Okay, now we have your online participants too. The first one is, I will call Arsenio Lourenço. With the poster No-Hermitian Heidelberg System with PT Symmetry. Hello, Arsenio, can you hear us? Hello?
Yes, yes.
Please, Arsenio, you can start.
Okay, thank you. Hi, everyone. I'm Arsenio Lourenço, and I'm a postdoc in the group of Professor Tommaso Macri from UFRN in Natal. This work has the collaborations of the experimental group at the University of Stockholm, led by Professor Marcus Henrich. This title of the poster is No-Hermitian Dynamics and PT Symmetry Working in Interacting Mesoscopic Readback Platforms. We have a question from Teresa Paiva. She asked, can you motivate the use of a no-emission Antonian? So no-emission system can approximately describe the quantum dynamics open systems. In particular, in this work, we studied the no-emission Antonians with Parrot and the time reversal symmetries. There were no PT symmetry. This class of Ramtonians presents a phase transition, which is characterized by the presence of real eigenvalues in the PT symmetric phase and the complex or imaginary eigenvalues in the PT broke phase. We studied the dissipative dynamics of the short range and the long range interactive particles for a three-level system composed by two Rydberg state and the ground state. We thought that the PT phase transition occur when we change the coupling strength in the interacting between the particles and the decay rates of Rydberg states. We also followed the phase transition. We studied the system from flow cave theory, and we also say that the dynamics of this no emission systems change which phase. In the PT symmetric phase, the dynamics range between 0 and 1. But in the PT broken phase, we have the exceptional growth occur, which is a typical behavior. And we also studied the physical population of the systems. In the PT broken phase, we long have the exceptional growth of the systems. So thank you for opportunity. Thank you for attention.
Okay, thank you, Arsenio. Is there more questions in the audience or not? Okay, thank you very much, Arsenio.
Thank you.
Okay, now you have Jacopo D'Alberto, who is the poster Study of a 2D Bose-Einstein condensates mixtures in quantum Monte Carlo methods. Sorry.
Hello, can you hear me?
Hello, Jacopo, yes. Just a minute, I will find your poster. Okay, please, Jacopo.
Good afternoon, everybody. I'm Jacopo D'Alberto. I'm a first-year PhD student at the University of Milan in Italy. I would like to briefly discuss my work, which is entitled Study of a Two-Dimensional Bose-Fermi Mixture with Quantum Monte Carlo Methods. This is essentially my master thesis degree work with Professor Pier Biagio Pieri and Dr. Gianluca Bertaina. So essentially, we perform a quantum Monte Carlo study of this novel many-body system, which is an ultra-cold gas made up by both bosons and fermions, with both Bose-Fermi and Bose-Bose repulsive interaction. We perform two types of quantum Monte Carlo simulation. In particular, we use variational Monte Carlo technique and fixed node diffusion Monte Carlo. Just to say some words, we compare our quantum Monte Carlo results with perturbative predictions obtained by Professor Pieri, And we obtain a good agreement with these predictions in the weak coupling region. So now I would like to answer to the question by Leandro, which we do not really understand the ansatz that I used for the wave function. So essentially, the choice of the wave function in quantum Monte Carlo simulations is a very crucial point. In literature, it is used to describe this Bose-Fermi mixture, a just translator wave function, which is composed by two terms. These two terms are essentially a Slater determinant and a Jastrow term. The Slater determinant is necessary because we have fermions in this mixture, so we need to take into account the antisymmetry due to their presence. And then we have the Jastrow terms, which encodes the pair correlation between bosons and fermions and bosons and bosons. So essentially, the Jastrow term is a product of factors that I called F in the poster. And these factors are the solutions of a two-body problem with proper periodic boundary conditions. So this is the answer to Leandro's question. Then there is a comment by Lucas Madeira about the bosonic clusters. If I could comment more. During our simulations, essentially we observe some peculiarity in our results when we go to the strong Bose-Fermi coupling limit. Essentially, we have large fluctuation in the energy, and this is always not a good sign. We have the idea that maybe due to the strong Bose-Fermi repulsion, the bosons can cluster together and form some clusters. So we perform a qualitative analysis. So we look for the pair distribution function, and we observe that essentially that when we have a strong Bose-Fermi repulsion, the bosons feel an effective attraction and they cluster together. This is maybe an effect due to the finite size of the system. We are sure that we lose our homogeneity in the system for strong Bose-Fermi repulsion, but we do not have time to explore in details this phase separation. So I hope it's all clear. If there are any other questions, I'm here to answer.
Okay. Is there another questions here? Okay. No more questions. Thank you, Jacopo.
Thank you very much.
Thank you very much.
Bye.
Now you have Mario Henrique Donato.
Hi.
Hello.
Hello. Can everybody listen to me?
Oh, okay, Mario. Just found your poster here, but you can start present yourself.
Okay, I'm Mario, and I'm a PhD student at San Carlos Physics Institute, where you are now. And here I have my work, which I called Synthetic Gauge Properties of the Quantum Excited States in Spinor BC Systems. For starters, this is an early stage work, and I'm working on it right now, and I'm going to tell you a little bit about what it is about. So, In particular, I was interested in studying synthetic gauge fields that naturally emerge in spinor BC systems. Well, for those who are not familiar with, spinor BCs are Bose-Einstein condensates of particles in a mixture of spin states, and I would say remarkably, due to properties related to the spin structure of the order parameter, which is the mathematical object that describes the system, there is the emergence of synthetic gauge fields, and these fields are analogous to the usual electromagnetic potentials we usually study in electromagnetism. Like we see here, the vector potential A and the scalar potential phi down below. So, in this work, I try to investigate what is the effects of quantum excitations on these particular gauge fields when we go beyond this mean field description that is explained in this slide. And Monica, can you go to the next slide, please? Thank you very much. Where I use a Bogoliubov description of the excitations in terms of a quantum field, so that by studying the structure of the current, the density current of the condensate, I try to analyze what is the equivalent vector potential of this in these excitations when there are quantum fluctuations in the system, like we see here above the acknowledgements. And what I could conclude at this early stage is that when I do an assumption like this in the current, I'm with this particular expression for the vector potential, I actually have a pseudo gauge field in the sense that I'm not solving the problem exactly, because when I have these quantum fluctuations, these excited states, I have actually a set of gauge fields for each mode of fluctuation. And now I'm going to answer Monica's question. And could you explain what would be a non-trivial gauge field in a quantum system? And Monica, thank you very much for asking. And in this work, I use non-trivial gauge field to indicate that these fields, A and phi, generated a non-zero synthetic electromagnetic field. We say electric field or a magnetic field, synthetic electric or a magnetic field. And I would say that in particular, these fields, they in several cases, they can, they are a way to explain some topological and symmetric properties of these systems. And I have here, why studying quantum fluctuations of these fields? And I answer that I believe that it's probably useful or a simpler way to describe the symmetrical and topological properties of quantum fluctuation that I believe exists. And I'm going to continue study, and well, that's a teaser for my future works. Thank you.
Okay, Mario, thank you. Sorry, you could not project all the slides. Sorry about that.
No, it's okay, it's okay. Thank you very much, Monica.
Okay, is there more questions? If not, let's thank Mario again. Thank you.
Thank you very much.
Our next participant will be Mateusz Bożeński. Mateusz, can you listen?
Monica,
Oi, Thalita.
Monica, can you hear me?
Yes.
Okay, I think we don't have more participants.
Oh, it's not time for more. Okay, let's then for the next sections. It's okay?
Yes, it is, but it's not because of the time. It's because they aren't here.
Okay. Okay. Oh, thank you very much, everybody. Then let's thank you all the participants of this section then.